Yesterday we have seen introduction to your first chapter under the heading of sampling. We proved important result related with SRS, that is simple random sampling. That result says chance of selecting any specified unit at any specified draw is equal to select that unit at first draw. Answer is 1 by n. We also proved the chance of inclusion of that specified unit in the sample of size n taken from the population size capital N. We'll try to understand this proof by taking simple numerical example. Consider population with 5 elements A, B, C, D, E. Find the probability of selecting element D at third draw by using a method of without replacement. This example is taken to just illustrate about theorem, because in real life population never small like this. The reason of adopting sampling is that the population is very large. It is only for illustration. See what the solution says. We have population with 5 elements. We want to find probability of getting D unit in third draw. This equal to probability not getting D in previous 2 draws and means multiplication. Probability of getting D in third draw from remaining units. So this is our interested event, which can be written by 2 disjoint events like this. Not selecting at first draw is 1 minus, it is not dot, 1 minus 1 upon 5. This is a product of not selecting. Not selecting at second draw is 1 minus 1 by 4, because at second draw available elements are 4. At first draw available elements are 5. Multiply chance of selecting unit D at third. So at third draw available units are 3. So chance of selection is 1 by 3. If you simplify this expression, 1 minus 1 by 5 is 4 by 5. 1 minus 1 by 4 is 3 by 4. Multiply 1 by 3. It is just like your general expression, what I explained last lecture. This cancel with next denominator, this cancel with next denominator, and so on. Same thing happens here also. 4 cancel with denominator of the next term, 3 cancel with denominator of the next term, and the method continue for any number of population units and corresponding sample size. Finally, I got answer 1 by 5. For this particular example, 5 is nothing but population size. Hence, this numerical example illustrates the proof which I explained above. Let us see another result which is also important. In simple random sampling without replacement, show that every sample of size small n drawn from a finite population of size capital N has equal probability, that is chance, and that equal probability is 1 upon NCN. What this theorem says, what this statement says, it says that if you decided to study population with sample size small n, then there are many possibilities to select small n items from the population capital N items. So there are many possible samples. So every sample has equal chance to be selected, and that chance is given to be 1 upon NCN. See the proof of this. We have various probability for selecting units in SRSWOR as below. Probability of getting unit at first draw with population size n is 1 by n. Second draw 1 by n minus 1, because method is without replacement. What you select at first, not replace back. So second time there are n minus unit available. So probability is 1 upon n minus 1. It continue like this. For nth draw, element balance are n minus bracket n minus 1. So corresponding probability is 1 upon n minus small n minus minus become plus. So what are these? These are the probabilities selecting unit at various draws. Hence, probability of getting a sample of n units in a fixed order. Suppose this is the natural order, first, second, third, like that. So if I pick up this order, then what is the chance to select a sample of n units? It is a product of this probability. Now this is the answer for only one sequence of selection. So for n items, there will be n factorial possible sequences of selecting a sample. If I want to explain this, suppose I want to pick up 3 units, 1, 2, 3. So I will have 3 factorial sequences, 1, 2, 3, 1, 3, 2, 2, 1, 3, 2, 3, 1, 3, 1, 2, 3, 2, 1. So I can pick up 3 elements in different sequence, and that is 3 factorial. So in general, if I want to pick up n elements, I will make sequence of n factorial. So this is the probability for one of the sequence. Hence, probability of getting n units in the sample of any order in any sequence, n factorial multiplied by this probability. So if you try to simplify this now, n factorial, here it is a product term. So denominator, I start with n, multiply n minus 1, n minus 2, n minus n plus 1, it is there. This I took extra. n minus n, then n minus n minus 1, and I continue like this. So what I write in the denominator, I write in the numerator. They get cancelled to each other. So this continue till 1. This denominator also continue till 1. So it is an adjustment to get a simplification. Now if you look at the denominator, it starts with capital N, product keep on decreasing, and it goes till dot 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 1. So I can write denominator as factorial n, because that is the concept of factorial. For example, 5 factorial equals 5 multiply 4 multiply 3 multiply 2 multiply 1. Similarly, here I start with n, keep on decreasing 1 in product, and I stop at 1. So this product is nothing but factorial n. What about the numerator? Numerator the same thing. I begin with n minus n, multiply decreasing 1 till 1. So the numerator is n minus n factorial. So now this 3 factorial I multiplied. So n factorial multiply n minus n factorial divided by n factorial. So this is nothing but reverse of combination. So I can write this in the reverse form, 1 upon n factorial divided by this. So these 3 products represent combination formula NCN. And that is your answer of your second result. Chance of selecting a sample of size n from population capital N is 1 upon NCN. Very important result. Now to study in detail for making inferences from sample, we require certain notations. So firstly, we'll try to study notation and then we'll try to go ahead. Notations in sampling. We denote population units by capital U1, capital U2, dash dash capital UN. First unit, second unit, and so on, last unit. What do you mean by this notation? Suppose you are studying some social economic problem. You want to decide average income of families living in Pune city. So from corporation, I will get entire record of number of houses. That means number of families. So U1, I will say family 1, U2, family 2. Like this is the last family recorded with respective observed values as Y1, Y2, dash dash Yn. So Y1 stands for income of first family, Y2 capital stand for income of family number 2, and so on. So when I speak about population, usually my notation is by capital letters. So U stand for element, Y stand for value of that element. Now in parallel to this, we have sample units, small u1, small u2, small un. Now small u1 is the first element selected from entire population. So small u1 sometime may be capital U1 or it may be U2, it may be anything from this population. Not necessary capital U1 is a small u1, it may be. And like that for all the elements. With respect to observed values, small u1 takes value small y1, small u2 takes value small y2, dash small u1 takes values yn. Now with the help of these two notations, I define population mean capital Y bar. Total of all population values divided by number of units. Simple formula, what you study as the average. So this is the average of entire population for your characteristic under study. In this example, the characteristic is income. So this is average income of total Pune city. What is the population total? That is denoted by simply Y. An answer is obtained by number of unit in the population multiply average of the population. This gives you total income of Pune city. Population variance denoted by sigma square. So sigma square is the variance quantity and calculated by this formula summation I from 1 to n yi minus y bar whole square divided by capital N. You know from your first year this numerator can be simplified, and that formula is summation y square minus capital N times y bar square, simplified formula. Similarly, you have population mean sum of square, that is S square. Look, this formula and this formula, a small change. Instead of writing capital N, I write n minus 1. So if denominator is replaced as n minus 1, it is not a variance, it is labeled as mean sum of square and denoted by capital S square. These are the population quantities. Now we have similar sample quantity. Sample mean small y bar summation yi upon small n. Exactly parallel to this. Just put small letters. So it is very important in this paper to write capital Y and small y. So if you are writing a population quantities, you should write capital, and if you are writing a sample quantity, you should write a small. Sample variance is denoted by S square, not by sigma square. This is the basic difference in your knowledge as compared to with first year. So S square will be summation yi minus y bar entire bracket square upon n. Formula is parallel like this, but notation is small s square. This is small s square. Now you have sample mean sum of square, that is small s square. Just you have to cross this line. And as population quantity, it is also small n replaced by n minus 1, named as a sample mean sum of square. This is unbiased estimate of your population variance. Not this is an unbiased estimate. What is concept of estimate and unbiased estimate? Estimate, we try to calculate population quantity with the help of sample quantity. That function is called as an estimator. We try to predict population average by using the sample average. So sample mean is an estimator. for population mean. When it will be unbiased? If expected value of that estimator is coming exactly population quantity, then that is unbiased. If expectation is not coming to population quantity, it will be biased estimator. So this is the definition for unbiased estimator. A statistic T. So statistic is one of the terminology in a subject statistics. T is a function of sample values called as a statistic. This T I will call unbiased for population quantity theta if expected value of T comes to be theta. That is the definition of unbiased estimator. Let us see now estimator of population mean and population total in the method of SRSWR. That means, suppose you decided to get average income of Pune people and to get average total income of Pune people. You cannot go for entire population study. So how you can get these two answers? By using a sample that we want to study here. What is the theorem? Show that in case of SRSWR with replacement, the sample mean, that is small y bar, is an unbiased estimator of the population mean, capital Y bar. That means what I want to prove, expected value of y bar, small y bar, is capital Y bar. If I am able to prove this, so I can take sample mean as a prediction of population mean. N multiply sample mean is taken as unbiased estimator of population total, capital Y. Let us see proof of this. Expected value of small y bar is 1 upon n summation I1 to n expected value of yi. So this is equal to 1 by n summation, this summation j from 1 to n, capital N, y I multiply pj into I. So 1 by n summation I1 to n, or you can say j1 to n, here I1 to capital N, yi is a population quantity, and you know we proved selecting of ith unit at jth draw is same as selecting at the first draw. So this is nothing but summation of capital yi upon capital N, that is the total y bar. Now y bar is a fixed. For given population, this is the one number. So summation of this number keep on adding n time. So it is n time y bar, that n cancel with this n. So you get expected value of sample mean as a population mean. So you can write in word, therefore sample mean is unbiased estimator of population mean. I have alternative proof for this on this half part of the page. See how it looks. Expected value of y bar, same as this, is expected value of summation I from 1 to n yi upon n. N is a constant, you can take it out. Expected value of summation yi I1 to n. This and this step exactly same. I took constant outside, you can take it by knowledge of your first year. No change. Now here I did a change. 1 upon n summation as it is. Now this expectation of small yi. How I write? I write summation I1 to capital N because I don't know from which unit comes in the sample. So I write for every element of the population yi multiply pj I. That means what? If ith unit comes in the sample, there will be probability. If ith is not selected in the sample, probability will be 0. So this will be only for your n items. The rest calculation will be 0 if it is not selected. So this as it is, this probability we proved selecting ith unit at jth draw is 1 by n. So this summation capital yi upon n is y bar. Summation is for small, y bar is average. This is a constant. Sum of constant n time is n time y bar. N get cancelled. So expected value of y bar sample is population mean. Therefore, in SRSWR, sample mean is an unbiased estimator of population mean. Now consider expected value of capital N, y bar small. Capital N is a constant value, put it outside expectation. Expected value of small y bar, we just proved capital Y bar. So n time capital Y bar, by the formula, Y bar is total of population elements divided by n. If I take this left, it gives a total. So n time Y bar is nothing but total of population. And therefore, this statement says that n into sample mean gives estimate of population total. So estimator of population mean and population total under without replacement. I taught you two methods of sampling, with replacement and without replacement. What we did here, it is for with replacement. Same thing we are going to repeat for without replacement. So question may be asked for with replacement, question may be asked for without replacement. Let us see how the proof works for without replacement. Let us define indicator variable as AI equal 1 if ith population unit includes in sample. This AI takes value 0 if ith population unit not included in the sample. Here should be not. So if it is included, AI will be 1. If it is not included, it will be 0. That means it indicates whether element comes in sample or not comes. That's why called indicator variable. So consider expected value of y bar is expected value of summation yi upon n. N is a constant taken out. Expected value summation I1 to n. Here I write 1 to small n. Now here I write 1 to capital N because I take the help of indicator variable. If AI is 1, that means it represents the sample quantity. And if AI equal to 0, everything becomes 0. So this is the total of sample and this is also total of samples, but under the definition of this variable, because it is 1 if there is a sample unit, otherwise 0. So this is the sample total, and this is also sample total for those elements which are already selected in the sample. So now this expectation I took inside summation. This yi is a fixed value now, and this is a variable. So expectation goes to variable. So 1 upon n summation yi, ai takes two values. So expected value is value of variable with probability plus another value of variable with probability. So 1 multiplied including the probability unit and 0 multiplied not including. So this is 1 upon n summation yi, 1 multiply, and this I told you, chance of including ith unit in the sample of size small n divided by capital N, because we want sample size small n from the population. This small n gets cancelled with this small n. Finally, what remains? Summation yi divided by capital N, and that is a y bar. Hence, we proved under SRSWOR, expected value of sample mean is again a population mean. So in both methods, where it is with replacement or without replacement, in both cases, sample mean is unbiased estimator of population mean. Now, if I multiply capital N to sample mean, that gives me population total. Hence, expected value of n times small y bar is equal to n times expected value of small y bar. It is proved to be capital Y bar. N times capital Y bar is the sum of yi. By the notation, it is capital Y, and that is the population total.